Morning, guys. So I'm going to continue working some problems. This is another nodal analysis problem from test 1, and it has a dependent voltage source in it. It's a voltage-dependent voltage source. So we're going to work this real quick, and I'm going to work this one the slow way, just to give you a little more of a fundamental view of how to work these circuits. So first thing we're going to do is we're going to label all our nodes that are important. So we have 3 nodes in this circuit, and let's see how many unknowns we have. So we know that's 12 volts relative to ground, and we know this one we'll just call V1, that's an unknown, and we'll call this one Vx since that's how it was defined in the problem. Alright, so we have 2 unknowns, and so we need to write 2 equations to describe this this little circuit right here. So as you can see, whenever you have a voltage source between 2 nodes, it's a supernode. So I'm going to highlight the supernode for you. So this is our supernode right here. And so whenever you have a supernode, you kind of have a gimme. So we'll call this gimme supernode internal, and we'll just write it out. So for this supernode, we can say V1 minus Vx is equal to 2Vx. And since we want to put everything that is not a constant on the left side of the equation, we'll go ahead and rewrite this as V1 minus 3Vx. I just brought the 2Vx over to the left side, and that's equal to 0. That's one equation. We need 2 equations and 2 unknowns. So the next equation, we'll call that one supernode external, and basically this one will be the sum of all the currents entering and exiting out of the supernode. So we'll start off by writing the equations for that one, and that's going to be V1 minus 12 volts divided by 1K, and V1 minus the 0, which is the ground right here, and we'll write that one over 1K. And I'm doing this kind of the long way. Obviously, you know the 0 there is going to go away. I'm just doing that for illustration purposes. And then the next one is on the right side. That's going to be Vx over minus 0 over 1K. And then we have another, we have a current, and so because we're assuming that the currents are all leaving out of this, like so, because we're writing Vx minus 0, Vx, V1 minus 12, we're assuming it's leaving, then because this 2 milliamp source is entering, this is going to be a negative 2 milliamps. And that's all also equal to 0, thanks to Mr. Kirchhoff. So if we simplify this, you'll see that we have 2V1, and then we have a, let's see, we have 1Vx, oops, 1Vx, and we also have a minus 12 over K and a minus 2 milliamps. So that's going to end up being 14 milliamps if we move it to the other side. Okay, so the next thing we do is we write this into our matrix, and we'll say V1 times Vx, and V1 and Vx is going to be equal to, we have a 1, we'll call this V1, call this Vx, and then we have a negative 3. We're going to invert that and multiply it by the constants. And then for this one we have a 2 and a 1, and we have 14 milliamps over there. So when you plug that into your calculator, V1 and Vx becomes something. Let me go check. So I did this in MATLAB on my iPad, and I got 6 and 2. I'll go back here, and we got 6 and 2. So now we know what V1 and Vx is. So it's asking us to find the power supplied, meaning the power coming out of this 12-volt supply. Power supplied by the 12-volt source. So if we're going to look at it that way, we want to define the current as going in this direction. So to do that, we'll say 12 volts minus V1, which we know is 6 volts, divided by 1K. And that should give us, let's call this I. We'll call that I12 volt. That's equal to I12 volt. And so that's going to be equal to 6 milliamps. And we know the voltage supplied by the 12 volt source, obviously. And we know the equation for power is equal to current times voltage. So that's just 6 milliamps times 12 volts. And that's going to be equal to 72 milliwatts. And that's supplied because we defined our current as leaving. So it's supplying the circuit with 72 milliwatts of power.